Hello, this is Nefi Varela, and in this video, I'm going to talk about venous return. And this is going to explain the exchange of liquids and nutrients that are going to flow around our body, and everything's going to start here at these structures that we call capillaries, okay? So we're going to have the arterial side, and we have the venous end. Both of them have capillaries and are divided by this that is called the interstitial space, okay? So in our arterial side, we will have these structures named precapillary sphincters. Those are like other sphincters that we have in our body. They are going to be smooth muscles, and they're going to regulate a flow of things, okay? In this case, of blood. And so we're going to have blood coming in thanks to the main arterial pressure. And well, those are gonna close or open. It's like that door in the supermarket that are gonna close or open when someone stands next to it. And what's gonna be those things that are gonna make this open? It's gonna be potassium, ADP, carbon dioxide, and hydrogen. Okay, so those, in the presence of those, are gonna be like those doors in the supermarket that are gonna let these two open. Okay, so here we're going to have some driving forces, some pressures that are going to influence liquid to go inside or outside of the artery. Okay, the first one is going to be hydrostatic pressure. Hydrostatic pressure is like how much water is pushing water to go outside. Since those are like permeable for water. This membrane is permeable for water, so the pressure that we have from this like arterial pressure is gonna cause water to go out, and we're gonna call it hydrostatic pressure. This is gonna be 30 millimeters of mercury, so it's gonna cause water to go out. The other pressure that I'm gonna describe is named blood colloid osmotic pressure, or BCOP. This is gonna be regulated by a protein named albumin. Albumin, it's a colloid. It has like a colloid appearance. It's also big, so it's not permeable to the other side of the membrane. As we learned in the first unit, water likes to party. So water is gonna go to the side with the greatest number of solutes, okay? So in this case, water wants to go to the inside of these arteries. So we're gonna have a pressure of 28 millimeters of mercury of water coming inside. Again, these colloids are also gonna push water out. We're gonna call it ECOP, or interstitial colloid osmotic pressure. And that one is gonna be 8 millimeters of mercury. And also we're gonna have these lymphatic vessels. Lymphatic vessels are gonna absorb excessive water, so they're gonna work as a vacuum somehow. And because they're like sucking things, this is gonna have a negative pressure of 3 millimeters of mercury. So we're gonna call this IFP. Okay, so as we can see, we have three forces taking liquid to the interstitial space: hydrostatic pressure, ECOP, and IFP. And the only one that is taking like liquid to the inside, water to the inside, is gonna be BCOP. So if we add these numbers together, the pressure that is gonna take water to the inside is gonna have a total of 28 millimeters of mercury. And taking it out, we're gonna have 41, adding HP, ICOP, IFP, 38, and 3, 41. So as we see, we have more water leaving the artery than letting it come in, okay? So as you can see, we have a difference. This number is bigger. So we have more water going to the interstitial space. So now what's gonna happen here, okay? Now this HP at the part, Spanglish, of the venous end is gonna decrease significantly. So in case of being 30 mmH millimeters of mercury, now we're gonna have 10. Okay, so that means that we don't have as much water going inside. Okay, these for some like anatomical things in the venous end compared to the arteries. Okay, BCOP is gonna be about the same, 28 millimeters of mercury, and ICOP is gonna be the same. Again, we have also this IFP, the lymphatic vessels. So if we add everything together, again, we're gonna have a total of 28 coming in. But compared with the other one, because the HP, the hydrostatic pressure, was way lower than the other one, it's just gonna add to 21. that it means that it's letting more water to come in compared to the arterial side. So as we can see, we have water leaving the arterial side in the interstitial, like the arterial side going to the interstitial space that is going to be absorbed in the venous end because of those pressures, because hydrostatic pressure is less than in the arterial side. So again, hydrostatic pressure here is going to be 30, B cup is going to be 28, I cup is going to be 8, IFP 3 for the lymphatic vessels. And here is going to be 10, 28, 8, and minus 3. Similar, the only difference, HP. Okay, so that's going to regulate how much water it's going outside, is going in. But in some situations, some things can cause something named edema. Edema means accumulation of water in the interstitial space. This can cause abnormality like pathologies as is sweating. Okay, so what can cause this? For example, first, I have four things, sorry, that are gonna cause edema that I know. The first one is the increase of hydrostatic pressure. So if we increase this number, instead of being, for example, 30, we take it up to 60, we're going to have a lot of water going inside. So water is going to start accumulating, and we're going to have more water accumulating here than that we are absorbing. So that's going to make fluids accumulate in that part. Second part, increased permeability of cells and walls, and walls of vessels. That can happen when we cut ourselves, when we burn. That can compromise our tissues and let the albumin that we said previously that are colloids, and because our colloids are big and they cannot leave the arteries, that's gonna make them be able to go to the interstitial space. So the osmotic pressure is gonna vary, and we're gonna see less water going inside, since we are gonna have more albumin distributed here in the interstitial space in the inside of the artery. So we are gonna decrease the amount of water that is going to the inside of the artery. So more water is gonna accumulate in the interstitial space. The third one, lymphatic system blockage or breakdown. For example, this can be caused by a disease named elephantitis that is caused by a microbe that is gonna like somehow obstruct or destroy this. So we're gonna stop that vacuum. And again, because this is responsible of like sucking water, water is gonna accumulate. In the other hand, for example, if we increase the pressure of lymphatic vessels, the only thing that we're gonna have is like more water going to the limbs, the lymphocytes. So not a big deal, okay? And the other one is osmotic edema. Osmotic edema, as I said, this is like B cup and I cup is something regulated by osmosis. So if we dilute our blood, if we dilute our plasma by water, for example, or decreasing albumin, so we're gonna have less osmotic pressure. Less water will want to go to the inside of the artery. So somehow, again, it's gonna accumulate more in the interstitial space. So again, just to summarize, it's gonna be the increased osmotic pressure, increased permeability of the cells and walls of vessels that can be created by a cut or by burning, lymphatic system blockage or breakdown that can be caused by a microbe, as is the case of elephantitis. So we stop our vacuum, and osmotic edema, we dilute our body. So our plasma, so we're gonna have less osmotic pressure, we're gonna decrease our B cup, and as consequence, we're gonna accumulate more liquid in the interstitial space. So that's venous return. This is the first part, and in the next video, I'm gonna describe some cool things as are the photoreceptors, the RAS system, and other ways as our body regulates blood pressure. So I hope you like it, and today's my birthday, so this is a super special video. See you guys.